I outlined the model I used to produce the following results in the document. Here in this video, I wanted to talk about the outcomes of the simulations themselves. Now, the first thing I wanted to show you was just the variety of phenomena you see in this model. I'll first show you examples of how the initial conditions settled in the heat equation, then the behaviour seen in the wave equation. This is reflective of how the simulation was run, first through the heat equation, then the wave equation. In all of these cases, the only thing changing is the seed used for the random initial conditions. Everything else is constant. Here you can see some settle to one vacuum state, a kink, an anti-kink, and any combination of such. When running the simulations, I let all of these settle until t equals 10. T equals 10, what, is a mystery that may or may not ever be answered, because I'm a mathematician and it's a fundamental law of nature for mathematicians to never work in units. Some of these settled pretty quickly, so I cut them short here to save everyone the boredom of watching a line not move. On the other hand, some didn't quite settle even after reaching t equals 10, which is why some of them look like they've been cut off, because they were. Moving on to the wave part of the simulation, their behaviour is even more varied. Some of them are particularly exhilarating, like this one here. Clearly it settled quite comfortably in the heat equation, whereas this one didn't quite make it and has a bit of a wobble. Stationary kink, wobbly anti-kink. These two are coexisting quite happily. Whereas these kinks are a bit more unhappy with their neighbours. Some of them take their time, really take their time. This one has a bit of a kerfuffle before doing a little slide to the right. I only looked at 10 samples and simulated a relatively small region, and even then I got this much variety. I can say something different for almost all of them. Maybe not this one, but this got me excited because it showed that in this model you don't have to put in solitons to get them. But there are quite a few flaws to this model, and I was wondering if one of my many crude approaches were the cause to this pleasing outcome. So I did another set of simulations, this time changing R, my random initial conditions boundary, to see if how I was setting up the simulation was encouraging what I wanted. I used seed 6 for these simulations because it was the one that I thought was most interesting. It was the one that did a little side dance to the right. And I wanted to see if I still got these structures with different initial conditions. Here are the outcomes side by side in ascending orders of magnitude of R from top to bottom, left to right. I know the text is tiny, but you don't need to read it to see what happens. You can see that they all settle at varying speeds, but all to a vaguely similar structure. But this minute difference in settling results in vastly different behaviours in the wave equation. I mean, one is a stationary vacuum state and another has 3 moving kinks. Anyone that knows anything to do with dynamical systems can see that this is a chaotic system, i.e. its behaviour is highly sensitive to initial conditions. I did think about trying to make a bifurcation diagram, but I didn't even know where to begin with regards to what my axes would be. So in situations such as these, I like to think that it's the thought that counts. Regardless, we still see solitons form, even when starting with incredibly small fluctuations. I even ran the simulations for an order of magnitude smaller than what I am showing, and get essentially the same outcome as 10 to the minus 3. So why am I doing all this? What is the point? Well, There is a popular school of thought in the physics community that the most fundamental object is a field, and everything, particles, forces, all spring from fields. So if we can make a model that mimics our world with the fields that exist in reality, we could investigate things like how massive structures in our universe form and what the Big Bang looked like. Think of my random initial conditions as tiny fluctuations in the field, which then spiral to its own order, forming solitons, which are analogous to particles. This is similar to if the Big Bang started from a fluctuation in a quantum field, that could then lead to particles forming, which will in turn eventually build the universe we see today. I hope that you have found at least some of this interesting and you've enjoyed watching my simulations as much as I have enjoyed making them, which was mostly except for the occasional bout of frustration. Thank you.